Hi, this is Sally's Book Club. Tune in daily as we explore the world's greatest books for you. Today we're diving into the book, Does God Play Dice? Oh, dice, those cubes we roll in games? This metaphor is all about randomness, suggesting God plays dice with the universe. It's essentially asking whether creation was random or predetermined. Our macroscopic world appears stable and objective, but zoom into the quantum realm and uncertainty reigns. That's quantum mechanics. Though seemingly abstract, quantum mechanics is one of 20th century physics' twin pillars. The other being relativity. Your smartphones? Think quantum mechanics for those. This book chronicles the history of quantum mechanics. It follows legendary scientists Planck, Einstein, Bohr, Heisenberg, Schrödinger, Hawking, and their quantum debates. Why Schrödinger called a cat torturer? How did Einstein lose arguments to Bohr? What's this about parallel worlds? All these answers await in this book. The publisher added mystery by keeping the author anonymous initially. Clever marketing gimmick. Actually, author Chao Tianyuan was an 80s kid writing this during college in Hong Kong. He masterfully transformed complex science into thrilling narratives. This book has outsold all Chinese science titles except A Brief History of Time. Quantum tales are that gripping. I'll break it down through three key threads: the light-nature debate, atomic model development, and quantum state interpretations. Quantum mechanics began with understanding light's essence. Back in the 1600s, two theories emerged. Particle theory saw light as tiny matter bits. Wave theory proposed light as vibrations through hypothetical ether. So, particles or waves? This debate lasted over 2 centuries. Newton, champion of particle theory, demonstrated dispersion. White light splitting into rainbow colors through a prism. What does this mean? Newton believed white light contained mixed color particles that separated through prisms. Newton's particle theory dominated, though wave theory had experimental support too. In early 1800s, Thomas Young created the double slit experiment, placing paper with parallel slits between light source and screen. The light passing through slits created alternating bright or dark bands, interference patterns. This proved light's wave nature. Dark areas where peaks and troughs canceled out. Bright areas where peaks reinforced each other. Wave theory now prevailed over particle theory. Physicists were still examining light through macroscopic phenomena. Little did they know, deeper light studies would unlock quantum mechanics' doorway to the microscopic world. Let's fast forward to late 19th century. Growing interest in thermal radiation. Long observed, heated iron glows dark red, then orange-yellow, color relating to emitted light frequency. This showed heated iron's radiation energy changes with temperature. But how exactly? 1900, German physicist Max Planck formulated the energy-temperature relationship. His equation required energy to exist in discrete quanta, like steps, like with quantum as smallest unit. But Planck, trapped in classical physics mindset, initially rejected his quantum child. Classical physics insisted energy was infinitely divisible. Einstein became quantum theory's first champion. In 1905, 26-year-old Einstein used quantum concepts to explain photoelectric effect, foundation of modern solar power. He proposed light energy exists in discrete packets called photons. Wait, light coming in particles? Isn't this particle theory reborn? And particle theory thus regained prominence. The old rivals, particle and wave theories, clashed again. France, 1924. Young physicist de Broglie proposed wave-particle duality, light as both wave and particle, finally resolving the centuries-old debate. Not just light, electrons too possess wave properties. De Broglie's matter-wave concept extended duality to all particles. His revolutionary dissertation earned him a doctorate. After experimental confirmation of electron waves, he won the 1929 Nobel Prize. At just 37, he proved all quantum entities are simultaneously waves and particles. This shattered classical physics. Newtonian either-or understanding was fundamentally flawed. The entire material world required quantum rewriting. Physics needed new foundations. How then to describe the quantum realm? We needed atomic models revealing inner structure, nucleus and electrons. Quantum models must explain electron orbits and nuclear relationships. Now let's examine atomic model development. Late 19th century physics saw multiple breakthroughs. Röntgen's 1895 X-rays, first Nobel Physics Prize, Becquerel's radioactivity, Curie's uranium studies, all pointing to nuclear structure. J.J. Thomson's 1897 electron discovery launched atomic structure research. Thomson's plum pudding model, electrons embedded in atoms like raisins in dough. He envisioned orbital rings around nuclei, electrons orbiting like planets. In 1913, Rutherford student Bohr introduced quantization through spectroscopy. He proposed electrons occupy discrete energy levels like stairs. Orbital transitions emit or absorb spectral lines. Bohr's atomic model perfectly explained hydrogen spectra, but it had fatal limitations. It failed with helium's 2 electrons or hydrogen molecules. This showed Bohr's model was merely the quantum revolution's prelude. Though obsolete scientifically, Bohr's orbital imagery remains iconic in pop science, revealing our visual bias versus scientific rigor. The revolution continued. Bohr kept pushing forward. In 1921 Copenhagen, Bohr established his institute, attracting global talents. Bohr became quantum's leader. The Copenhagen School's core included Heisenberg, Pauli, Dirac, all under 30 during breakthroughs, earning quantum its boys' physics nickname, thus dubbed boys' physics humorously. A philosophy emerged: only observable quantities hold meaning. Heisenberg developed matrix mechanics using observable data tables. It finally calculated helium's spectra, Bohr model's former failure. In 1925, 24-year-old Heisenberg achieved this, making 36-year-old Schrödinger seem ancient. Undeterred, Schrödinger formulated his wave equation using de Broglie's concepts. This mathematical framework using calculus had been familiar since Newton's time. Like calculating pendulums or circular motion in school, all could be expressed as wave equations. The equation introduced wave functions, treating electrons as vibrating strings with quantized modes, enabling spectral calculations. Schrödinger proved quantum wave mechanics could reconcile with classical physics. Fascinatingly, matrix mechanics and wave mechanics, seemingly different, yielded identical results. Schrödinger, Pauli, Jordan, Dirac mathematically proved their equivalence. With these mathematical tools, quantum mechanics could precisely calculate material structures. Let's pause to appreciate this harmony, then brace ourselves for quantum's core paradoxes. Part 3. The debate about quantum state's fundamental nature. With matrix or wave mechanics established, particle models were built, but interpretation wars began. Consensus. Mathematical equations reflected physical reality. Dispute. What reality? First, Copenhagen interpretation's 3 pillars. 1. Born's probability interpretation. Schrödinger's wave function. Continuous spatial distribution. What's its physical meaning? Schrödinger thought electrons spread like butter on bread. Continuous wave substance. But Born, Heisenberg's mentor, argued differently. Wave functions show probability distribution. Electrons don't smear out but appear randomly per probability waves. Ironically, Schrödinger initially misunderstood his own equation. Physicists joked Schrödinger's equation was smarter than its creator. Take the double-slit experiment. When firing particles one by one, photons, electrons, all show interference patterns. This reveals each particle's wave-like behavior, even when isolated. The paradox: how does a single particle know to create wave pattern? When few particles are emitted, their positions on screen appear completely random. Here one moment, they're the next. But with enough particles, interference patterns emerge. Individual randomness collectively follows Schrödinger's wave function distribution. We can't predict single particle positions, only probability distributions. Asking, which slit did the electron pass through, becomes meaningless in quantum terms. Quantum mechanics requires abandoning classical trajectory concepts. Many physicists struggled with this paradigm shift, as we'll see. Second pillar, Heisenberg's uncertainty principle. In matrix mechanics, a times B is not equal to B times A if A and B represent position or momentum. Measurement order matters. Measuring position first disturbs momentum, vice versa. All measurements require interaction. Example, photons used to observe particles inevitably alter their state. This interaction fundamentally changes the measured system. Simultaneous, precise measurement of conjugate variables is impossible. Absolute precision doesn't exist. Originally called indeterminacy principle, now better understood as fundamental uncertainty. Classical physics, objective measurement illusion, gets shattered. Measurement always disturbs quantum systems. Quantum mechanics demands specifying measurement methods before discussing physical quantities. The problem runs deeper. Quantum theory fundamentally overturns classical worldview. Uncertainty isn't measurement limitation. It's inherent in nature. Electrons don't have precise positions or momenta, only probability clouds. Finally, Bohr's complementarity principle completes the triad. In Newton's era, the universe was seen as a vast, precise machine. Scientists believed cosmic fate was predetermined from creation's first moment. Laplace famously claimed complete initial knowledge could predict all future events. Schrödinger's probabilities and uncertainty principle reveal cosmic dice rolls. Initial conditions, fundamentally unknowable. Matter's inherent uncertainty stems from wave-particle duality. How then does random quantum behavior create our orderly reality? Suns rise predictably. No quantum tunneling through sidewalks. Your devices display crisp images, not quantum blur. Macroscopic stability from microscopic chaos. How do probabilistic particles form precise reality? Bohr's 1928 complementarity principle addressed this. Phenomena only meaningful within measurement contexts. A horse's color depends on the observer, red to you, green to colorblind friend. Through sunglasses, it shifts again, reality shaped by observation tools. Photons behave as particles in Compton effects, waves in double-slit experiments. Bohr's observer-dependent reality. More rejected classical objectivity, observer and observed form inseparable whole. Wave or particle duality. Mutually exclusive yet complementary aspects unified at higher reality. Embracing contradictory properties provides complete quantum understanding. Bohr's complementarity plus Heisenberg's uncertainty plus Born's probability equals Copenhagen interpretation's triune core. This orthodox interpretation has dominated quantum textbooks, shaping humanity's cosmic understanding. The Copenhagen interpretation reveals quantum reality's inherent randomness. No absolute objectivity exists. Only observable reality matters, the reality we participate in. This view unsettled classical physicists. Even Einstein rejected it despite contributing to quantum theory. Einstein argued, a physics without causality is unthinkable. We can't grant particles mysterious free will. Don't mistake Einstein as anti-quantum. He pioneered photons, lasers, and Bose-Einstein condensates. His deep involvement made his critiques particularly insightful. Bohr's faction opposed determinism's abandonment, not quantum mechanics itself. Einstein famously declared, "God doesn't play dice," maintaining this stance till death. He believed quantum theory, even if correct, was incomplete. Quantum randomness might hide deeper mechanisms yet undiscovered. Legendary Solvay conferences became Einstein versus Bohr showdowns. Einstein's morning thought experiments challenged Copenhagen logic. Bohr's evening counterarguments preserved quantum orthodoxy. Their clash refined quantum foundations through rigorous debate. Einstein's critiques ultimately strengthened the theory he questioned. The famous quantum entanglement concept emerged from this debate, also called EPR paradox. Einstein aimed to disprove Copenhagen interpretation through reductio ad absurdum, assuming its validity to reach illogical conclusions. He imagined a spin-zero particle splitting into two particles, flying apart with opposite spins. Visualize one spinning left, the other right. Copenhagen interpretation says both remain undefined until observed. Observing one instantly defines its state, and through conservation laws, the other state too. But how do distant particles communicate faster than light? This apparent FTL signaling violates relativity, Einstein's main objection. Bohr countered. Einstein mistakenly applied classical particle concepts. Regardless of separation, they remain a single quantum entity until measurement. The particles aren't independent. Observation affects both simultaneously. This demands abandoning classical objectivity to grasp quantum reality. Ironically, Einstein's mistake birthed quantum entanglement, his unintended quantum legacy. Their debate lasted until Einstein's 1955 death. 7 years later, Bohr died, still pondering Einstein's challenges. Their intellectual duel remains science's greatest rivalry. Einstein wasn't alone. Schrödinger joined him in opposition. Schrödinger's cat thought experiment mocked quantum weirdness by scaling it to macro-world absurdity. The Copenhagen interpretation states, particles exist in superposition until observed. Wave function collapse determines definite states. Einstein retorted, does the moon cease existing when nobody looks? Schrödinger imagined a sealed box containing a cat, poison gas, radioactive material, and hammer. Radioactive decay triggers hammer to smash poison vial, killing the cat. For Copenhagen view, before observation, decay exists in superposition. Thus, the cat exists in dead or alive superposition until box opens. Observation collapses superposition into definite state, alive or dead. This quantum cat became physics' most famous paradox, mocking interpretation flaws. Hawking joked, when I hear Schrödinger's cat, I reach for my gun, ending its quantum torment. Why does macro-scale reality conflict with quantum rules? Copenhagen's observer dependence blurs subject or object boundaries, a conceptual leap beyond classical experience. If observation itself is physical, does consciousness influence reality? Does consciousness shape cosmic evolution? Debates birthed alternative interpretations. Many worlds theory proposes universe splits during observation, all possibilities realized in parallel realities. Like seeing the cat alive here, another parallel world chose differently. There we'd find it dead. This cosmic splitting birthed sci-fi's beloved parallel worlds trope. Despite interpretive debates, quantum mechanics remains physics's most successful applied theory. It unified physics and established our fundamental material understanding. Applications span semiconductors, lasers, nuclear power, even finance. See Soros's quantum fund. No quantum theory, no modern world as we know it. Feeling confused? Don't worry. As Bohr said, if quantum mechanics doesn't shock you, you haven't understood it. Feynman later quipped, nobody understands quantum mechanics, whether God plays dice or not. Quantum mechanics demands your attention. You're the universe's observer, participant, and co-creator. That's Does God Play Dice? Key takeaways below. Tuning tomorrow for more.